Hi, ladies and gentlemen. So in the previous lesson, we started talking about pressure, fluid pressure, and how it basically envelops any sort of object that's within it. And that could be inside a liquid or inside the air itself. Today, we're going to be talking about buoyancy and Archimedes' principle. And buoyancy, you guys have all experienced it whenever you go swimming. I mean, whenever you go swimming, you've noticed you seem to weigh less than water. But does your mass actually change? No, of course not. So why is it that when you're in the water, you feel lighter? And this is why we start talking about the buoyant force. So any object that's in water, if we talk about pressure, is going to feel fluid pressure from all sides. Now, if you remember, our formula for pressure was P equals PO plus rho GH. The fluid pressure ultimately is dependent on the depth, how deep you are inside the water. So if the water is up to a certain level, if I were to ask you, how does the pressure here and here compare? Well, since they're at exactly the same depth, you'd have the exact same pressure, and they would ultimately cancel each other out. But if you look at the top versus the bottom pressure is going to be greater than the top pressure because there's more depth. So there's more pressure here, there's less pressure there. So because of the difference in pressure, there's ultimately going to be a force that's acting on the box because of the difference in pressure itself. And this difference in pressure will ultimately generate a force upwards. And we'll call that the buoyant force, FB. Now, Archimedes was a genius Greek scientist way, way, way back in the day, which we've talked about before in optics when he invented the Archimedes death ray. But he also came up with the principle about buoyancy itself. And he ultimately realized that the buoyant force was equal to the weight of the water displaced by the object. The buoyant force is equal to the weight of the water displaced. So if I write that actually as the formula, the buoyant force, FB, is equal to the weight of the water, M times G, of course, but we're going to use rho V G. Rho, of course, means density, and we're talking about the density of the fluid. So when we talk about rho here, we're talking about the density of the fluid, and V is the volume displaced by the object. Now, if you remember from our first lesson, so this is the fluid, that's the volume. Density times volume itself, remember density is equal to mass over volume. Density times volume is the same thing as saying mass. So really the weight of the water, M times G, or rho Vg, is equal to the buoyant force. Okay, so if you take a look at this example here, let me move this bar out of the way. Okay, we have an object floating within the water, and you can see, according to the free body diagram, there's a buoyant force going up, and there's the weight of the object, the mg of the object, going down. So let's actually go over to, let's see, my animation over here. In here, we have a cube floating in water. When the cube is moved into the water. Hopefully you guys saw that the green arrow over here got larger than before, okay? Now, when the cube goes out of the water, if I actually let this play out, oh, sorry, I forgot to. Well, in this case, the cube sunk. But if I make the cube rise, okay, here we go. Now watch the green arrow. The green arrow got smaller. Why did the buoyant force change when the cube came out of the water? Well, if you look carefully, the cube is only halfway inside the water now. The volume displaced by the cube is less. So therefore, the buoyant force got weaker. But if I move it back down into the water, you can see the buoyant force increases as well. Okay. Now, I need you guys to understand that the mass of the material of the object itself has no effect on how much buoyant force there is. I can make the force more dense or less dense. When I make it less dense, you guys can see that the weight is getting smaller. When I make it more dense, the weight's getting larger. But if the size of the object doesn't change, if the volume doesn't change, then the buoyant force doesn't change as well. Because ultimately, the buoyant force is just equal to the weight of the water that's taken up by the space of the cube itself. Okay. So hopefully you guys realize that if I just change the object's volume then, by making it larger or making it smaller, I change the buoyant force itself. Okay? Just remember, buoyant force is FB equals to rho VG. So if the liquid itself becomes more dense as well, that will increase the buoyant force. You guys can see, is it increase the density or is it decrease in the density? That completely changes how much buoyant force there is. Because the shape of the object, if the water inside were to be heavier, then the buoyant force would be greater as well. And we are going to ultimately be able to start doing sigma F equals ma equations with this type of problem. Because when well, in this example, if I were to just let it go, we can see that the object is sinking. So overall, it has a downward acceleration. So therefore, you would get mg minus fb is equal to ma. And you would be able to solve for the acceleration of the object while it's sinking. A lot of times, they may end up not even giving you the mass of the object, but they'll give you the density of the object as well. But we're going to do some AP problems, and we'll see that. But keep in mind of sigma F is equal to ma. If I make my object lighter with less and less mass, you guys again can see that the buoyant force now is greater than the weight. The object is less dense than the fluid. So if I were to let this go, it's going to rise upward positive. So you end up with FB minus mg equals to ma. Okay? But once it's floating, okay, notice it's not moving anymore. A is equal to 0. So when A is equal to 0, when it's floating, FB will automatically equal to mg. Okay? So I'll put a little star there. When floating. Okay. So if we come back to our diagram over here, again, I'll mention that you must make sure you draw a free body diagram before you solve the problem. And let's actually do a practice problem now. We have a 70-kilogram statue lying at the bottom of a lake. Its volume is 3 times 10 to the 4th centimeters cubed. So keep in mind that the density of the water is something you should always know. is 1,000. And if we were to draw a free body diagram on the statue, we have mg going down, and we'd be trying to lift it. Well, in this case, we're just talking about the buoyant force on the object. So if we're talking about the buoyant force on the object itself, Fv is equal to rho Vg. Density of water is 1,000. The volume of the object is stated to be 3 times 10 to the 4th centimeters cubed. Now remember, we don't use centimeters cubed, we would use meters cubed. And to convert from centimeters cubed to meters cubed, we would divide by 100 3 times to convert it over. So this would actually end up being 0.03 meters cubed times gravity, and you would end up with 300 newtons. So this ultimately is the buoyant force itself. Of course, this isn't enough to actually lift up the statue because we know that the weight of the statue is going to equal to 700 newtons. But if we were actually trying to lift the object, therefore 700 minus 300, the tension force needed to lift the object, if we were to draw an upward Ft, Ft would equal simply to 400 newtons. We'll take a look at one more example problem. This is later in the packet, where we have a block attached to a spring. The block of wood has a density of 650 kilograms per meter cubed, and there's a lot of information missing here, but let's list it out first. The mass of the object, I'll write MO instead of, as opposed to, because it's the object itself, is equal to 5 kilograms. The density of the object as opposed to the fluid or the water itself would be 650 kilogram per meter cubed. If you take a look, they show the block buoyant force is pulling up on the spring, but it's held back by the spring itself and, of course, its weight. But it is in equilibrium. So if they wanted us to, they're asking us how much did the spring stretch? Well, we just set up a sigma F equation. It's not moving because it's all balanced, which means that FD will equal to mg plus kx. And ultimately, we're looking for what x is. Now, the problem is we are going to have a little bit of trouble solving for FB because we know FB is equal to rho Vg. We don't know the volume of the object. However, we do have the mass and the density, and knowing that density is equal to mass over volume, volume would simply be mass divided by density. So 5 divided by 650, which gives us 0.0077 meters cubed. Okay, so now we know the volume of the object, which happens to be exactly the same as the volume displaced because it is completely submerged. So when I do FB minus equals mg plus kx, so FB is rho Vg equals to mg plus k times x. So we would end up with 1,000, I'm just going to leave out units here in the interest of space, times 0.0077 times 10 is equal to, well, mg would just be 50 plus k times, and they said it's stretched, sorry, they said that the k is 160 newtons per meter times delta x. So now, keeping this all in mind, if I plug this into my calculator, I would get the answer to be delta x is equal to 0.169 meters. Okay, so ultimately you can see that it's just a basic force problem, and we will do more AP questions later on. Now, the thing is, when Archimedes was actually trying to understand about the idea of buoyancy, he was actually trying to answer a question that was posed to him by his king. You see, the king had received a gift of a golden crown from his enemies, and the king, not really trusting his enemies, wanted to know, is this crown really made out of gold? But I can't damage it because that would be an insult to my rivals. So he asked Archimedes, determine if this crown is gold. And Archimedes, not really knowing what to do, was racking his brain, trying to figure out how to do this. And one day, as he actually sat in his bathtub and he noticed the water level rising, he understood the idea of volume displacement. He realized, eureka moment. He jumped out of the bathtub, stark naked, ran down the hallways, yelling, "Eureka, Eureka," which means, I've got it, and because he actually figured out how to solve for the density of the crown and to understand, is it gold? And this is the idea of specific gravity. And this was with him using buoyant force. You see, specific gravity is really just a ratio of the object to the fluid that it's submerged in. So if we talk about object to a fluid, so when we talk about the object's force or its weight, mg, as opposed to the force of the fluid, that would be the buoyant force, every object, everything has some sort of ratio, and we'll create a different number for specific gravity. In fact, if we take mg and take FB and break into its actual formulas, FB is density of the fluid times the volume displaced times gravity, while m times g, m is really just density times volume as well, but in this case, talking about density of the object times volume times gravity. And you realize, wait, it's the same volume, same gravity. Specific gravity is just a ratio of density of the object to density of the fluid. And this ratio will determine whether or not an object is going to float. If it's more dense than the water, it's going to sink. If it's less dense, it's going to float. But keep in mind this ratio for specific gravity, and we're going to walk through the problem that Archimedes himself kind of figured out as well. Okay. So we have a crown with a mass of 14.7 kilograms. It was submerged in water, and when it was submerged, a scale that's attached to the crown says that it now only has a mass of 13.4 kilograms. Now, did the mass of the crown actually change? No. The scale is just giving a reading of basically the tension force. So if you take a look at the very first diagram, the scale over here is the reading for the tension force. And it said that the tension force was equal to, well, since it's 14.7 kilograms, it's Ft is equal to 147 newtons. And of course, since this entire thing is at rest, that means that the mg, that the actual weight of the crown, has to be 147 newtons as well. Now, when the crown is submerged in water, however, okay, Ft is no longer the only force. The crown, of course, doesn't change weight. It's still 147 newtons. But now they say Ft has a reading of 134 newtons. What must be happening is that the water itself is providing an additional buoyant force, Fb. 147 minus 134 is equal to 13 newtons. Okay? So if I were to look through the questions, what is the actual weight of the crown? The actual weight of the crown would be 147 newtons, because that's what they measured in air. Okay, there's nothing else helping to support it. So the buoyant force is going to be the actual weight subtracted by the supposed reading and we get 13 newtons. So if I was to calculate the specific gravity, it would be mg over the object over the fluid which is ultimately also equal to the density of the object over the density of the fluid. So the weight was 147 over 13 newtons. Now, we don't know what the density of the object is. This is what Archimedes was trying to solve for. But he knew that water had a density of 1,000. It had already been confirmed. So when you cross-multiply this, and you work it out, he found that the density of the crown that he had was equal to 11,307 kilograms per meter cubed, which, by the way, happens to be the density of lead, okay? Meaning that the crown was not actually made out of gold. Now, this is just one example of how a specific gravity problem might look. However, specific gravity can also be used in another way. If the specific gravity is greater than 1, we already said that the object is going to sink. But if the specific gravity is less than 1, it's going to float. And that's just density, like the density lab that you guys have done before. But what's interesting is that the specific gravity is also equal to the percent submerged under the fluid. Meaning that if your specific gravity is 0.8, then the object would be 80% below the water line and 20% above the water line. So a couple examples. An iceberg. Ice has a specific gravity that's very close to 1. In fact, the specific gravity, I believe, is, off the top of my head, 0.93 maybe, okay? Which means that's 93% underwater. And as you guys can see over here, the majority of the iceberg is underwater. So when the Titanic was traveling through the waters and they have not really seen the tip of the iceberg, you see, icebergs are dangerous because if you have a ship that's sailing and they think, oh, maybe the ice isn't that big, well, I didn't draw a very big ship. If I drew a much bigger ship, okay, the ship is coming along, they think, oh, it's just a small patch of ice, we should easily be able to clear past it. In reality, it's this gigantic boulder of ice that's just floating in the water. Whenever you have a drink, you've noticed that ice cubes barely float up top because they're 93% submerged underneath. However, if you take something with a smaller specific gravity, let's say like a plastic bottle, since it's mostly air, has a specific gravity of maybe 0.05, a very, very tiny number, which means that it's only 5% submerged, okay? So the ratio of the specific gravity itself, density of the object versus density of the fluid, will always allow you to solve for how much is actually submerged. So if we take a look at this example question over here, we have a raft made out of wood with a density of 600 kilograms per meter cubed. They're giving you the area and the volume. Now, these are actually all very good questions, but we're first going to solve for the specific gravity to determine what percentage is submerged. Then we'll get to A parts A and B and C. So specific gravity is equal to density of the object over density of the fluid. The wood was 600 Water has a density of 1,000, as we already know, which means you get 0.6, or in other words, 60% submerged under the water. They ask us also to solve for the weight of the raft. Notice they give me the density of wood. Density of the object is 600. The area was 5.7, and the volume was equal to 0.6. If I want to solve for the actual weight of the raft itself, well, I know the density, I know the volume. Density is equal to mass over volume, so M is equal to 600 times 0.6, which is equal to 360 kilograms. So the mg would equal to 3,600 newtons. If I was looking for the buoyant force, the question is how much buoyant force would there be? And you could, of course, use rho Vg as well. Let's actually erase this for a moment. So if we're solving for the buoyant force, there's a hard way and there's an easy way, by the way, at this point. We could use FB rho Vg, and this would be the density of the fluid, so that would be 1,000. Now the thing is, what is the actual volume? Because the raft is no longer completely submerged. It would have to be the volume that's actually inside the water, this part right over there, which means that if it was 60% submerged, it would be 60% of the volume. So it would be 0.6 times the volume of 0.6 meters cubed times 10, which of course is equal to 3,600 newtons. Because when it's floating, FB will equal to mg. And if they ask us, let me just clear this, knowing that volume is equal to area times height, how much height is actually submerged below? Well, we know volume is equal to length times width times height. That's how we get area times height. We know the volume, we know the area, so therefore the height is equal to 0.6 divided by 5.7, which is equal to 0.105 meters. And if it's 60% submerged, if you multiply that by 0.6, we get the actual height submerged would be 0.063. Okay, and that's the answer for part C. If we take a look at this question, the North American continent has a density of 2,800 and floats in the mantle of the Earth. As you guys may have learned in earth science, the continents are all floating on the mantle, which is liquid. The mantle has an average density of 3,300 kilograms per meter cubed. What fraction of the continent is submerged? So in this case, again, we can use specific gravity, density of the object over density of the fluid, and we will have 2,800 divided by 3,300, which would give me an answer of 0.85, which means that's 85% submerged. And if it's 85% submerged, they're asking what height of the continent is above the mantle. Well, the height was equal to 35 kilometers. So if it's 85% submerged, that means it's 15% above. The answer would be 5.25 kilometers. Okay, so ultimately, buoyant force is the force of the fluid that is pushing on an object upward, and it doesn't have to be water. It could even be air itself. whenever you see a balloon float upwards, right? When we see a balloon float upwards, that's because all around the balloon is air. And air is the fluid which has a density of 1.29 kilograms per meter cubed, which is very, very, very small. But keep in mind that it's still going to be a large enough force to counteract the weight of the balloon and the weight of the gas inside the balloon. So helium is the gas that's most commonly used because it is less dense than air itself, and you can calculate the rate of a balloon floating upwards based on FB minus mg of the gas inside the balloon and mg of the balloon itself. And we will do some practice problems with that in class. So this is buoyant force, this is specific gravity, and this concludes hydrostatics.